Okay. Okay. So first, we're going to make the assumption to solve this that we have only dry gas no liquid, and that means a few things. So that means no condensate, we have no water, and we have also no production chemicals. Always, even if it's very dry, we always have some dropout either of oil, okay, or we have some dropout of water, because the gas is saturated with water at reservoir conditions, or we need to inject something for we will see later, but for flow assurance, to avoid corrosion, we have some production chemicals which are liquid. Okay, so we are assuming here only dry gas because we don't want to take that into account. Okay, because our equations are not the equations that we will use are not suitable for that. Okay, the next assumption we're going to make is we're going to say all wells are identical. Okay, that means that they have the same production, okay, and they have exactly the same characteristics. Okay, and that's an approximation we can make. Typically all of them will be different, but if we are at an early stage of field development, typically we say, well, all of them will be the same. Okay. Another thing we're going to say is that templates, just also to honor that constraint, templates are located symmetrically from the plemb. Okay, that means that the pipes are exactly the same length, the pipes have exactly the same topology, are exactly the same. Okay? So this approximation actually causes a very important simplification to our problem. Okay. The thing is, I don't have to solve, and we are going to see later what we are going to take this assumption away, but basically this should be right if they are all symmetrical, or they should be actually longer, right? I guess. Okay, that all of them will be different. I have to compute the network, but because of this assumption, I can say I can just analyze this flow path, okay, the transportation in the flow line. Here I will have the full rate of the field. Okay. Then I go just on one. I don't have to go to each template, or I don't have to see what happens in each template, because all of them are identical. Simply can just look into one of them, right? And here the Q will be Q of the template, which is Q of the field divided by the number of templates. And then I can go just to one well. I don't have to study each well in the system. Okay, so here I have the Q of the well, which is the Q of the field divided by the number of templates times the number of wells per template. Okay, so that's exactly what the system that I'm going to analyze. I'm going to see this pipe. Remember our analog, we have to go from the reservoir to the bottom hole. Okay, then I go to the bottom hole to the wellhead, and then I go from there to the choke. Here I have a choke, usually is located in the template. Okay. Then I have flow in a flow line and flow in a pipeline. Okay, so let's make that thing here, that sketch. We have from PR, which is common for all of them, to PWF, from PWF all the way to wellhead. Okay, this pressure, I'm going to call it P template, and this will be P plem. Okay. So that's what we call the IPR, that's what we call the TPR. Then we have the P template all the way to P plem. That is a flow line performance relationship. And finally, P plem to P separator, this will be a pipeline performance relationship. Okay. F stands for flow line, that's a flow line, and that here is a pipeline. Okay, so I need all of those elements, or I need to know how the drop is to see if that rate will be feasible or not. Okay. Sorry, I need here one more thing, right? The choke. Forgetting the choke. That will be from B wellhead to P template. I have the choke. Okay, so let's go one by one to each. What equations do we need? And we need one more, right? So we have here simulating all of the parts in our system, but we need one more thing, right, that we are forgetting. That was the reservoir. Okay, which is connected to each one of these wells. So the equation IPR, it tells me a function between Q gas at standard conditions, okay, remember, as a function of PR and PWF. Okay. The TPR gives me, again, is the rate as a function of PWF and P wellhead. Okay. The choke is, again, a function of PWH, P template, and also the choke opening, CO. The flow line is a function of P template and P plem, and then the pipeline is a function of P plem and P separator. Okay. So that's all. We are going to neglect for now temperature. Okay, we are looking simply at pressure, because we know pressure represents energy. Okay, also temperature represents energy, but we will say pressure, and we want two pressure nodes, and we have to see how much is going to lose from the reservoir all the way to the separator. Okay, if that energy balance is positive, that means I can produce the rate. If that energy balance is negative, that means I cannot produce the rate. Okay, in a kind of a simplistic way. And then we need for the reservoir. What do we need for the reservoir? Okay, reservoir, we are going to assume is a tank at some particular reservoir pressure. And what do I need? The main parameter that I'm interested in is this PR, right? And I want to see how that's changing with time, okay? But not only time, that depends not so much on time, but depends how much I have drained, how much fluids I have produced, okay? So there we're going to use the dry gas material balance. Okay, which is, I guess all of you remember by heart. You repeat it every time before you go to bed. Okay, initial ZR over ZI, yes, 1 minus the recovery factor, which is the GP over G. Okay, and that's the recovery factor. Yep, that correct? Okay, so that's the equation. Kind of all petroleum engineers learn almost kind of the in the first lectures. Okay, how is the pressure of the reservoir of the tank declining with how much I drain out of the tank? Okay, and so it's a function of how much is I have recovered, I have removed from the tank. Okay. So let's see how to use that equation. Okay, we have to say, so how do I use it? This guy usually measure it, right? In exploration, I'm able to measure that pressure. If I do a well test, I'm able to measure that pressure. The G, that's speculation, right? A bit. I have some volumes that I have mapped in my seismic. I have petrophysics to correlate with the layers. I have a geologist making some interpretation of what is the volume. But so this is a highly uncertain value. Okay. But we still have, if everybody agrees, we say we will see later how to calculate that number. But basically we say we believe we have so much that's the most likely value. Okay, that's the mean. The mode actually. Okay. How much we have produced? That is something we will see now how we do that, but that will depend on if the rates are feasible or not, right? I assume a rate, I see if it's feasible. If it's feasible, then it means I can produce it. Okay, so that will be a function of the rate. Okay, with time. And I have different ways to integrate that rate. Now Z, what is Z? Okay, the gas compressibility factor, gas deviation factor. Okay, and you remember we had a chart. Okay, that looks like that. And how do I read that chart? Just to remember, what do we need to read it? Okay, we need, in this axis is reduced pressure. What is reduced pressure? Pressure divided by critical, right? So that means every reservoir pressure I simply divide by the critical pressure of the gas. Okay, and the gas we assume it has some. So let's write that down. This is just a refreshment. So Z is a function of PR and TR, right? And PR is, sorry, not R, not big R, okay? Reduced, okay, not reservoir pressure. Avoid confusion. Let's use R. Okay, so that will be reservoir pressure divided by critical pressure. Okay, and critical pressure is typically a function of simply the composition of the gas. Okay. And also the same thing for TR. TR is reservoir temperature divided by critical temperature, where that critical temperature is also a function of gas composition. Okay, depending how much methane, how much ethane, how much propane it has the different the mixture has a different critical conditions. Okay, so you fix those. So here you have Z. That's where you read it. Okay, so you have pressure, and then all of these lines, they are for different temperature, reduced temperature. Okay, so you go with your pressure you have, let's say it's 12, and your reduced temperature you have, let's say it's 1.4. Okay, and then you go to the left and you read the value of Z. Yeah, that clear? No big surprise here. So what does it mean in terms of this equation? Let's say we have GP, we have the recovery factor, right? And we have initial pressure, so I can find ZI. But what does it mean in this equation if I want to find now the new pressure? It's implicit, right? It's an implicit equation. Because this Z that I have here, we already mentioned it depends on pressure. So this Z depends on the same pressure, the same thing that I'm trying to calculate. Okay? So this equation, let's put it here. Is implicit. Okay, so then a kind of a suitable procedure is I will assume, so given I have given recovery factor, okay, assume PR. Okay, I assume. Then from here, with PR, compute ZR, okay, and then I verify that PR minus PRI, ZR, ZI, okay? I have to verify with the value that I assumed and the value that I read from the chart with that assumed value, that will be 0, okay? If not, then I have to repeat. I have to go back to this step. Okay? I have to assume another reservoir pressure, I have to read another set, and then I have to check again this error. Okay? Equal to 0, or we say practically has to be less or equal than a tolerance. Okay, that I define. Yeah? So in our exercise, we're going to make, because we don't want to have this manual process to read from the chart. Okay, we don't want to do that manually because we might have to iterate and try with different pressures, and that will be kind of we want to avoid manual intervention. Okay. So for that, we're going to use. You can read about it. I will not say. Okay, you go to that source, and here they show the chart. Okay, and here they have okay, the procedure where to, if you want to calculate that chart with equation. Okay, so that's the procedure we're going to use, and actually it's already pre-programmed for you, so you don't have to do it. But if you want to understand it, how it is done, I suggest you to read that section in the monograph of Curtis. Okay, so just we're not going to be using the chart, we're going to be using this procedure, and it has been programmed for you already in Excel. And that procedure, I think it was done by Paul Yarborough. Okay, you have to solve kind of a bit of an ugly equation. Okay, but you can read more about it in okay, that's what we are going to use. Okay, approximation, that's equation approximation to the set chart, okay, which was made by Standing and Katz. Another thing we're going to use is we're going to use to predict T critical and P critical, which we need for the pseudo reduced pressure, we're going to use Sutton correlations. Okay, which are given also someplace here. Okay, Sutton are these two equations. Critical pressure of hydrocarbon, which is a function of the specific gravity of the gas. Okay? And also, specific gravity of, only specific gravity of gas. I'm just trying to show you where the equations more or less come from, so you don't we don't start using them, just, without knowing where they come from. Okay, and how do I calculate the specific gravity of the gas? Is molecular weight of the gas divided by the molecular weight of air. Okay, which is 28.97, I think. Okay, so any gas that you have, and how do I calculate the molecular weight of the gas? Is the sum between 1 for all components of the mole fraction of that component times the molecular weight of that component. Okay, so if you have a gas which is made of certain components, you take that whole list and you multiply the mole fraction by its molecular weight. Okay, so now we are done with that equation. Okay, that's what we are going to use to predict how pressure will decline with time, with how much I have produced, which in a way is a function of time. Okay, Qg is a function of time. And we know we have some implicitness on that equation, but we are going to see how to go around it. Okay, we don't want this to be iterating in each step, but we know it is an implicit equation. Okay, next step, the IPR, right? Next we have to go PR. Now we have PR, we go to PWF, and that is with an IPR equation. The IPR equation we are going to be using is the low pressure dry gas equation. Okay, which looks like Qg is a function of Cr, which is a back pressure coefficient, inflow coefficient, and PR squared, PWF squared to the power of n. Okay, and that's called the back pressure exponent. Okay, it came by two sources. First, that equation came measured empirically in the field. Okay, they saw that when they plotted, all of them more or less follow on that trend for one particular well, but then it was demonstrated theoretically, where that equation came from. Okay, inflow coefficient, that's typically a function of TR, of permeability, the height of the layer, what else? Skin factor, let's call it skin factor. Okay, and N is simply saying if the flow is highly turbulent or highly laminar. Okay, if it's laminar, it should be N should be closer to 1, and if it's turbulent, Forchheimer flow, it should be close to 0.5, right? And if you plot that equation, it's going to look, if you say PWF and rate, for 0 rate you have simply reservoir pressure, and if you lower lower bottom hole pressure, then you will see a trend like that. It will be a curve like that. Okay. Other comments, be careful, that's only for low pressure. We're going to be using here for relatively high pressure, so it's valid for low pressure. And it's also for the pseudo steady state regime. Okay, also called boundary dominated flow. Are all of you familiar with pseudo steady state? What does it mean? Who's not? Who needs some clarification? Nobody? You want to get to the exercise quick, right? Okay, if you, I'm not going to discuss it here, but if you have any doubt, you can go to my compendium. Okay, if you plot, you read that it's explained here, page 37. Okay, so basically, if you initially the well is closed and you start producing, the pressure in this bound will lower dramatically, and then you have a big peak because the rest of the formation haven't felt yet that you start producing. Okay, but when this pressure is lower, the pressure next to it, which is higher, it will cause a flow of fluid towards the wellbore. Okay? And then it will start to propagate that front slowly until you reach the bound. Okay? So that equation that I showed you is not good between T1 and T3, just when you open and when it's reaching the bound. Okay? But after it reached the bound, that equation applies. Okay? So then from all subsequent times, that is a good approximation. Okay? Reservoir pressure, but not for this period. The thing is that period is usually short for medium to high permeabilities. Okay, here you have some times that are calculated. So really, it's not significant for the whole production horizon. Okay, if you say your field is producing for 20 years, probably will be in transient, a low percentage of that time. Okay, we have our IPR equation. Later, hopefully, you're going to work with a more accurate equation for high pressure. Next, so let's make the comment here. This is page 37 of compendium. Okay. Next was TPR, right? We have to go PWF all the way to PWH, and for that we are going to use dry gas tubing equation. Which says that QG is CT PWH Okay, I think so. Okay, so that's called the tubing coefficient. That's called the elevation coefficient, not the skin. Okay, it's the same S, but this one is called the elevation coefficient. So that guy is supposed to capture for friction losses, and this guy is supposed to capture for hydrostatic losses. How that equation was derived, again, we're not going to do it here in class. This is not a production course, but you can go to, I think the derivation that was made by Michael Golan, and you have it here. Okay, is Appendix A, page 157. Okay, and that was made by Michael Golan. So you start with Bernoulli equation, and then you have some variation of density because gas will change density with pressure. So you have to use the real gas equation with the deviation factor, and then you have to integrate that between bottom hole pressure and wellhead pressure. Okay, and that you end up with. So that's how it looks like. The equation, you see you have a bunch of factors. Let me copy that equation. So I also recommend you, if you want to know a bit more how that equation is derived. Okay, that's in page 156, Appendix A. Okay, you have here that elevation coefficient. PT means wellhead pressure. Tubing pressure is sometimes called. Average temperature. You have to have some temperature average between the bottom hole and the wellhead. C average, the set calculated at bottom hole, set calculated at wellhead, and averaged. So this equation is also a bit implicit. Molecular weight of air, R of the gas, standard conditions. Let's just verify. Okay, that's the equation. Okay. So what happens when flow rate is 0 on that equation? So if flow rate is 0, right, then CT doesn't matter anymore, the exponent doesn't matter anymore. Then you have that PWF will be equal to PWH e to the S okay, to divided by 2, right? Yes? You have to be awake, okay? Maybe I'm a bit, I make a mistake and then all of you are going to cry because I made a mistake. You're the guys that are supposed to be awake and watching my every step, okay? So, you see that so that pressure is simply the hydrostatic, okay? If you have no flow, that means that simply by the column of gas you have that the pressure at the bottom hole is greater than the pressure at the surface, okay? And you have some assumptions that I think all of that. Let's see, I think it's here someplace in the notes. What is CT? Okay, that's CT, and S is also someplace there. So let's. Okay, so if you make that approximation, CT, all of that is part of CT. And you see here you have the friction factor, so that's why I said it's the friction dominating part. You have the diameter of the tubing, you have the length of the tubing, and you have some properties. And then the S is where is the S? Here, okay. Okay, and I think I have, let me check. Okay. Okay, so that's how I have calculated for you. We're going to use some numbers and they are calculated with all of that input, okay, using those two expressions. I can also share with you that sheet if you want to make calculations for other conditions. Okay. Now, next step, we have already that equation, right? Next step, what do we have after? Wellhead? Okay, the choke, right? P template. That's a choke equation. And that for now, I will say we can live without that equation. Okay, I will say no need for equation. Okay, we will see now why, but let's say simply no, we don't need that equation. Okay, we know that it has some issues. It's non-linear. It's inaccurate. Okay, might be very inaccurate. So let's for now say we don't use that equation. Okay, and then let's say P template all the way to P plem. That's a flow line, right? And a flow line is essentially the tubing, right? It's essentially also a pipe. So here the tubing equation can be used for the flow line because it's essentially flow in a pipe, okay, which is the same thing derivation that we did for gas. Okay, one assumption we are going to make is horizontal pipeline or flow line. Okay. And then the tubing equation simplifies to QG C of the flow line P template squared minus P plem squared to the power of 0.5. Okay, if the flow line is horizontal. And that is because if you see here, S becomes, I think it becomes 0, okay? S becomes 0. And then we have to simplify the CT to get, for a horizontal line, which causes some issues, because here we have, if you see, we have 0, and we have here 1 minus 1, which is 0. Okay, so we have, it becomes kind of undefined. Okay, so we have to do some math trick. What do you do in that case if you have kind of an undefined expression? Okay, L'Hopital, this theorem you thought you will never hear again. Okay, but we have to use it here. 0, 0, we have to apply L'Hopital up and down, and then you get rid of that problem. Okay. So here I'm going to just put that quote. It's actually kind of nice. You don't use math just to make us suffer, but also you use it for something. And then for the pipeline, P plem all the way to P separator, we're going to use actually the same equation. Okay, we're going to use QG is CPL P plem minus P separator squared to the power of 0.5. Okay, now we have everything we need. Okay, we have how to change pressure with time or with rate. We have how to calculate the energy losses in the system. Okay, so now we have to have like a strategy how to how to make it. Okay, so let's make a tentative strategy before and then we take a break. Okay, so here we have this choke, and then we have the template at this condition, and then we have the flow line here, and here finally we have P separator. Okay, be aware the rates are different. The rates that I have here is the Q of the field, and here will be P plem. Okay. The rate that I have here is the Q of the template, okay, and here I have P template, okay, and the rate that I have here is actually the well rate. Okay, all of through this system I have the Q of the well. This will be PWH P bottom hole. Okay, because we have this symmetricity and all wells are identical. Okay, so that's why we can see at this it will be the same if you do it for well 1, 2, 3, 4. All of them will be exactly the same. Okay, so what I suggest to do is, we don't have this model, right? That's the only part missing in the puzzle. So what I suggest to do simply is take it out of the system, remove it, okay? And I'm going to calculate the energy, that means the pressure which is available here. I have a rate that I want to produce, right? Is this 20 million divided by the number of wells, okay? So I impose that rate here, and that rate will lose energy up to here, it will lose energy up to here, and then it will have some available energy, okay? Then I come with the same field rate from here to here, 20 million, okay? Then I come from here to here with like 6 point something million, okay? And then I obtain the required pressure, okay? That's the pressure that I have after I have losses in the formation and losses in the tubing, the available pressure that my reservoir can give me. And that pressure is the pressure that I require to flow this rate and this rate against separator, okay? So then I have to do a final checkup here, because that model I don't have. So when is that rate going to be feasible? Or I will be able to produce that rate? When this one, the energy that I have is more than the energy that I require, right? Because then I can simply use the choke to burn that energy, the excess energy that I have, okay? But when that pressure is lower than that pressure, I don't have enough energy, okay? What do I do then? Then the choke is not relevant anymore. Simply can have open choke, okay? Then the choke doesn't have to be modeled, okay? So let's try to summarize that approach. So we're going to fix the rate, okay? Calculate P wellhead from reservoir. And then you want to calculate P template from separator. So that means here I will add IPR and TPR, and here I will add the PPR and the FPR. Okay, and then you have to verify that P wellhead is greater than P template. That means that the rate is feasible. If, on the contrary, P wellhead is less than P template, then the rate is not feasible. And what do I have to do? Reduce the rate, right? I don't have any other choice. I have to reduce the rate to have more energy available in that point. Okay? Must be reduced. Okay, so let's now take another break, the last break, 15 minutes, and we come back and I just show you where are we going to solve it, a very brief introduction to XLVBA, and then we start solving it. Okay, so let's take a break.